So this video is still chapter 7. Notice I have chapter 7.5 though. Because if I was the author of our textbook, I would have put the first half of the chapter and then this half of the chapter in two separate chapters, chapter 7 and 8, let's say. Because they're very, very different topics. I'm not sure why they crammed it into one chapter, so I just kind of wanted to distinguish that for you by calling this chapter 7.5. Kind of taking a step back, saying we're kind of moving on to something new here. Now, in this half, we're going to go over mole conversions, percent composition, and empirical formulas. The only two new things that you're actually going to do is the percent comp and empirical formulas, because we've actually already done mole conversions. So the first one or two videos here are going to be done very, very quickly because they are review. If you need to go back and get the more detailed explanation, go back to chapter 3. Chapter 3 has the short or the more detailed, the longer video where I go through it more thoroughly. But because I've already done it, we'll go quick. So what is the mole? First of all, it's MOL for short. Not much of an abbreviation, but it is an abbreviation. All it is it's a counting unit, if you remember. And it's no different than the dozen. So when you think dozen, you think the word 12, or you think the number 12. You might think of counting like eggs by the dozen, donuts by the dozen. We do the same thing with atoms. It's just we count them by the mole, which is a much bigger number because atoms are much tinier. So we count them in big chunks, or chunks of a lot of them. So the mole is represented by this number, 6.02 times 10 to the 23rd. That's how many of anything are in a mole. You can count a mole of basketballs, a mole of pennies. However, it's such an absurdly large number that you don't count normal everyday objects that you deal with by the mole. But we do count atoms by the mole, and it comes in very, very handy. Because when we start doing chemical reactions like this, we're going to start talking about like 1 molecule of N2, or you'll hear me say 1 mole of N2. So like 1 mole of N2 reacts with 3 moles of hydrogen to form 2 moles of NH3, or ammonia. And if you look here, here's a mole of all of these different elements. So you can see a mole of these elements is actually a reasonable amount of that substance. It's a nice amount to work with in lab. Because a single atom's so tiny, you never work with just a single atom. You work with atoms more on the scale of a mole. You'd work with about this amount of carbon probably if you're doing a reaction, or this much zinc. These are common, more realistic amounts to work with. So that's why the mole is so handy. So the mole, here's how it works. If you've got a single molecule of water, it weighs 18 AMU. That's a single molecule. 1 oxygen, 2 hydrogens weighs about 18 AMU. If you have 1 mole of them, it will weigh 18 grams. So this number, 6.02 times 10 to the 23rd, connects these two numbers. It allows us to use the AMU that's found on the periodic table in terms of grams, which is it's a far more practical unit to work with because that's what our scales use. So Avogadro's number is the number of particles in 1 mole of a pure substance. We count atoms, formula units, and molecules by the mole. Remember, atoms are for elements, formula units are for ionic compounds, and molecules are for covalent compounds. So whenever we say a mole, we're talking about 6.02 times 10 to the 23rd particles per mole. It's this huge number. So again, we don't use it very much. It allows us to convert from moles to atoms, formula units, or molecules, which we don't actually really do in this class, just because it's not really that useful. What's more useful is that we actually go from grams to moles using Avogadro's number. So the mole, again, when we talk about formula units, that's for ionic compounds like NaCl. Remember, we call this a formula unit. 1 atom of copper. That's an element. And then if we talk about covalent compounds like water, we call this a molecule. So why are they useful? Because they allow us to convert. Why is the mole useful? It allows us to convert from concentration to mass to formula units, atoms, molecules, temperature, pressure, volume. Now we don't do this one really anymore. We used to. We cut it out to just make things simpler. This chapter will do a lot of this. Let's see here. In the future, we'll learn how to calculate concentration, and we will learn how to calculate pressure and temperature and volume of a gas, and moles comes in handy. So molar mass. Quick review on molar mass. Molar mass is the mass in grams of 1 mole of an element. It is found on the periodic table. So an example, carbon. If you look up carbon on the periodic table, it has a number of 12.011. Now what this means is that one atom of carbon has a mass of 12.011 AMU, or 1 mole of carbon has that same mass in grams. If you had a mole of carbon, it would have that mass in grams. So 1 mole of carbon, if you have this many of them, this many atoms, it will weigh this many grams. So that's why we say grams per mole. There's this many grams in 1 mole. So here's the molar mass of a bunch of different compounds, including the mass. So you can see a sample of water. 1 mole of water weighs 18 grams. 1 mole of sucrose. You got a mole of potassium dichromate and a mole of salt here. Now hints to find mass. You need the molar mass from the periodic table to get the molar mass. You'll look that up on the periodic table. When you do a mole conversion, the mole will equal 1. So wherever the mole is on your ladder, top or bottom, that's where the 1 will also go. So to add up molar mass, and again, I'm moving really fast. If you need to go back and refresh a little more, go back into the chapter 3 videos in the playlist on YouTube. But molar mass, you just add them up from the periodic table. So we'll keep on going here. It's the mass of 1 mole of a compound. Don't worry about sig figs. So here's an example. This is really what you need to know. If I give you KCl, the first thing you do is you list out the elements K and Cl. Then the next thing you do is you say how many of each are there in the formula. Next step is you look up the masses on the periodic table. Look up potassium and chlorine. You multiply it out. In this case, if there's more than 1, you'd have to double or triple or so forth there. Then you're going to add these 2 numbers, and then that is your molar mass of potassium chloride. So this tells me how many grams are in 1 mole of this compound. So if I had 1 mole of potassium chloride, if I wanted to get 1 mole, I'd go to the balance and I'd weigh out 74.551 grams of it. If I wanted 2 moles of it, well then I need 2 times this much. If I wanted a half a mole, I'd do 1/2 times this number. For this one, the next 2 examples, I'm going to let you do these on your own. If you need help with them, talk to me in class. Let me know if you need me to do an example or 2 in class. I want to make this video as quick as possible, and then I will spend more time on it in class if I need to. Same thing with this example. Do this one on your own. If you find yourself struggling with it, talk to me in class. Don't forget, this 2 distributes in. I am going to tell you 2 things here though. Barium, there's 1 of them because there's no number. Oxygen, in this case, there would be 2 of them. And then hydrogen, there would also be 2 of them because this 2 distributes in. I'll actually go back up to here. I am going to help you out with this just to make sure we refresh our memory on it. There's 1 copper. In this case, the 2 would multiply in. 2 times 1 is 2. 2 times 3 is 6 oxygen. And so the rest, you just look up the masses added up. Now, conversions, what you're going to do is you're going to use the molar mass to go from grams to moles. To do that, and this is the exact problem I did in chapter 3, so I will go a little quicker here. First thing you got to do is find the molar mass. This is dihydrogen monoxide, it's H2O. The molar mass of water, 1 mole, instead of adding it up for you, I'm just going to give it to you, 18.0148 grams per mole. If you add it up from the periodic table, 2 hydrogens, 1 oxygen, you'll get this. Now, here's how you actually do the molar mass, or the mole conversions. It says how many moles are contained in 34.5 grams. So you always start by taking the number given, 34.5 grams, and then I want you to put H2O in there as well. The next step is you take grams of H2O and you bring it down. Whatever unit is here, you bring it down. Leave the number behind, bring the units down. Then it says how many moles, so I want to go to moles of H2O. And then from there, if you remember, I briefly mentioned it, wherever the mole is, that's where the 1 goes. And then you say how many grams are in 1 mole? Well, there's 18.0148 grams in 1 mole that you looked up from the periodic table. Sorry, I need a quick drink of water. Now, at this point, when you set up these ladders, you multiply across the top, divide anything that's on the bottom. So I take 34.5 times 1 divided by 18.0148, or just go this divided by this. And grams divided by grams cancels out, so I am left with moles of H2O as my units. And if I divide this out, give me a second to get my calculator here. Hold on, 34.5 divided by 18.0148. I end up with 1 point, I'll write it up here, 1.1915. I only have 3 sig figs to work with here, so I have to cut this off here. I'm going to round this up to 1.92 moles of water. And that would be my final answer for a mole conversion. Now here, what is the mass of 2.3 moles of water? Same thing, you got to add up the molar mass of water. It's 18.0148 grams per mole. Then you set up your ladder. That was a nice straight horizontal line. 2.3 moles of water. You always take whatever is given and you put that in the top left of the ladder. Then you bring moles of water down. And you're going to go to grams of water because it says what is the mass. Mole gets the 1. How many grams are in 1 mole? It's this number. And then you're going to end up multiplying and then round to the right number of sig figs. Moles cancels. I'm left with grams of water on top. And if I do 2.3 times 18.0148, that gets me 41.4. So I'm just going to round that to 41 grams of H2O. Again, if you need extra help on these mole conversions, it's going to be very important moving forward. But I've already taught them once, so I made this video very, very quick as a refresher. It's not meant to be like your initial teaching of this. So make sure if you are not clear on this that you talk to me. So the next thing is going to be percent composition, which relies heavily on doing these mole conversions. So again, let me know if you have any questions, if I need to do extra problems with you.